unit ladder of weight W and length 4 meters. I need to put center mass there. That's the weight is W. End rests on a rough ground, horizontal ground. Okay, so there's got normal contact force here. I'll call it RA, and I've got a friction in there. And it's end against a smooth vertical wall. That means there's no friction. That means my normal contact force will come straight out here. That'll be RB. That is inclined to angle theta, yeah, or tan theta equals a half. If it gives me this, I mustn't work out what theta is in terms of the angle. Just keep with tan theta, I'll be okay. Small object of weight S, weight 2W is placed on the ladder at point C, 1 meter from A. A is here, it's 4 meters, that'll be 2 meters, so small weight is put in there, and that will be weight 2W. Yep, coefficient of friction is mu, so I'm going to put down mu equals something. I've got to show that mu is 2/3, so we'll have to work out what mu is. And it's in limiting equilibrium, therefore F lim equals mu r. I'll show this. Well, if I'm not sure about what I'm doing, then I'm going to resolve a couple of directions and take moments. Almost as soon as it gives you some lengths and stuff, then you're going to need to know, need to take some moments. So, first off, as part I, I'm going to resolve horizontally, and that will say that I've got F equals RB. F equals RB. I'm going to resolve upwards, and I'm going to get the upward forces. That's RA equals the downward forces 2W plus that will be 3W. And then I'm now going to take moments. Well, I've got F lim equals mu r, and this is down here, so that's RA and F. So I need to find out what RA is. That's 3W, got that already. So I know that bit, and now I need to find out what friction is. Well, actually, if I take moments about this point here, I'll only have RB, and RB equals F, so I'll be alright. I don't take moments about A, because that gets rid of two forces. I'm going to say that anti-clockwise moments equals clockwise moments. I've got RB is an anti-clockwise moment, it's going that way, so I'm going to get RB times my distance that will dot out here. This is the distance I'm talking about, and same as that, that will be 4 sine theta. So times by 4 sine theta, and that equals this one here, 2W, times that length 1, so that distance here is 1 cos theta, times by 1 cos theta, plus, and that will be W times by 2 cos theta. And so I'll say that RB times 4 sine theta equals, that's 2W cos theta, another 2W, that's 4W cos theta. So RB, divide both sides by that, will give you W, 4 divided by 4 is nothing, so cos theta over sine theta. And we know that sine theta over cos theta equals a half, so cos theta over sine theta equals 2. So that tells me that RB equals 2W, and from here, let's call it equation 1, from 1, that says that F equals 2W, and so we got F lim equals mu r, so mu equals F lim, just worked out, which equals, that's 2W, and R, this will be RA, we've worked out RA is 3W, so 3W, so that will be 2/3, which is what they wanted me to show. So now on to part 2. Okay, first off I need to draw a new picture of what it looks like. Lots of the forces remain the same. I still got W here. I still got normal contact force here. I'm going to call that RA still. Still got normal contact force here, RB. But now I've put a weight of AW here, so I'm going to get another AW there. I've got the weight of 2W is put, S is put down here, so I've got 2W there. Obviously still got friction coming in, and I think that's pretty much where we are. Again, if I'm not sure about what I'm going to do, I'm just going to resolve in both directions and then take moments. So to start with, I'll resolve upwards, and I get RA equals 2W there, plus W, plus AW. So I got RA equals 3W plus AW. Resolve horizontally. That will say that F equals RB. I don't even know what I need to find. Given it's in equilibrium, I've got F lim equals mu R, or mu R, because it's in equilibrium. Find the set of values, possible values of A. So I need to get A. I'm going to need to take moments. I'm actually going to take moments about A, because that will get rid of all three of these forces. So take moments about A, and as always, anti-clockwise moments equals clockwise moments. First thing I always write down. So what have I got? Anti-clockwise. It's exactly the same as I had before. It will be the RB. So that will be RB times by 4 sine theta. And there's nothing else which goes anti-clockwise, so that will equal the clockwise moments, which will be, I can put these together, so that'll be W plus AW times by this distance here, that length's 2, that's theta, so that'll be 2 cos theta times 2 cos theta. And so RB, if I divide both sides by cos theta times 4 sine theta over cos theta equals, bring 2 to front, 2 lots of W plus AW. That's tan theta. Tan theta is a half, so that's RB times 4 times a half, which equals 2W plus 2AW. And that will say that RB equals, that's 2 on the left hand side, divide both sides of 2, that is W plus AW. And from, if I call that equation 2, from 2, that means that W equals, so W plus AW equals F, that's the friction. We've got limiting friction, which is mu R, and so friction, W plus AW equals mu, just work that out, 2/3, times by R, that is R here, which is 3W plus AW. So 3W plus AW, and that's W plus AW equals 2/3 of 3W, will be 2W plus 2/3 of AW. That will give me 1/3 of AW, because I've got a whole AW here, minus 2/3 here, will equal W. Therefore, 1/3 of A equals 1. Therefore, A equals 3. And obviously, if I put on more than 3 on there, it would slip. So A has got to be less than or equal to 3. That's my solution here, running out of space. And that's 7 done.